P-H-Y, 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 P-H-Y. Physics. Welcome!
Welcome to another Honors Physics Camp lecture. Today we're going to be discussing Newton's laws of motion.
Wait, what?
No, Alex, not a newt in motion. I said Newton's laws of motion, as in Sir Isaac Newton's laws of motion.
Oh, I knew that.
Okay, Alex, make sure you take good notes and let's begin. Alex, what are you doing? That's not exactly how it works, Alex, but I'm glad that you're starting to remember who Isaac Newton was. He was a famous mathematician, physicist, and astronomer who developed major physics concepts that are often referred to as Newton's laws of motion. Good question, Alex. So the story goes that Isaac Newton was sitting under an apple tree when suddenly an apple fell on his head, which led him to the central ideas resulting in the laws of motion. Basically, this led to the development of three laws of motion, in which the first states, yes, Alex, glad that you remembered it, but you're missing an important piece of information, which is that an object will remain the same way unless acted upon an unbalanced force. The next is the second law, which states, yes, Alex, the second law deals with mass and acceleration in relation to force. Basically, it states that mass times acceleration equals force. And lastly, the third law states, you got it, Alex, the third law states that every action has an equal and opposite reaction.
Well, that's it. Have a great one.
No, Alex, not so fast. We're not done yet.
Oh, I knew that.
We need to fully understand each law, not just memorize their catchy phrases. So let's get started. Before we go into more details as to what Newton's first law of motion truly means, we must first understand a couple of key terms such as inertia, force, mass, and friction. Inertia, Alex, is basically the resistance of an object to change its motion or lack of. Yes, that's right, Alex. Inertia is basically the stubbornness of an object at rest to want to stay at rest, or the stubbornness of an object in motion to want to stay in motion, unless an outside force causes them to do so. I'm glad that sounds familiar to you, Alex, because we just mentioned it when we described Newton's first law of motion, which is why the first law is also known as the law of inertia. Basically, inertia is the stubbornness of an object to resist change. It simply wants to remain in its current state, whether it's in motion or at rest. I guess you could see it that way, Alex. Some objects do have more inertia than others, but it's because of their mass, not laziness, like in the case of your dog. For instance, let's compare this empty aquarium to this full aquarium. Which one do you think will have more inertia? That's right, Alex. The full aquarium would have more inertia. But why if they're the same object? Right again, Alex, the water results in more mass, which means it's going to be more difficult to make it move. Thus, the greater the mass, the greater the inertia the object has, meaning the greater the force that would be required to change its motion. This brings us to our next key term, which is force. What do you think force means? Not exactly, Alex. Muscle is not necessarily the equivalent of force. In physics, force is defined as an interaction on an object such as a pull or a push that may cause the object to change its motion when it's unbalanced. In other words, it's the ability to cause changes to an object's state of motion. Yes, that's right, Alex. Moving a couch would be a great example of both pulling and pushing forces on the object, which in this case is the couch. Notice that these forces have a direction either going against or towards the object to illustrate its interaction, which means that force is a Yes, you got it, Alex. Force is a vector, meaning it has both magnitude and direction. You need to also remember that physical quantities such as force use units for measurement, and in this case, force uses the unit known as newtons. Yes, Alex, just like that, which further illustrates the big impact Isaac Newton made in physics. Okay, Alex, enough with the couch. Instead, let's try to understand what balanced and unbalanced forces are. That's one way to look at it, Alex. Balanced forces are those whose net force equals zero. So, yes, they basically cancel each other out. Yes, Alex, that's right. If you and your friend were both pulling on the couch with the same amount of force, but to opposite directions, then the net force applied on this object would be zero, meaning the forces would be balanced. Thus, the object's state of motion would not change. In other words, it would stay as is. But what if you pull on the couch with a 2 Newton force to the right and your friend pushes on the couch to the right with a 2 Newton force? What would be the net force here? That's right, Alex. The net force would be 4 newtons to the right, or we could just say positive 4 newtons, meaning the forces would be unbalanced. So what does this mean? You got it, Alex. Unbalanced forces may cause objects to move, such as the case for this couch. That's right, Alex. You basically got the idea behind Newton's first law of motion. Basically, this law states that unless an unbalanced force acts on an object, that object should continue doing whatever it was currently doing. Thus, if it was in motion, it's going to remain in motion forever. Great question, Alex. Everyday objects in motion eventually slow down and become motionless without seeing an outside force acting on it. Why? Yes, Alex, there is a force that tends to act opposite to motion due to the resistance between two surfaces, which is known as friction. Now, keep in mind, Alex, that not all friction is the same. There are different types of friction based on the surfaces that the objects come in contact with. Thus, in most physics problems, we tend to just ignore friction or state that the scenario is in a frictionless surface so that we can focus our attention on other outside forces that may be acting on that object, which is causing it to change its state of motion. Yes, Alex, that's right. Unless an unbalanced force acted on it, it would continue to move. Okay, now that we understand these key terms, we can now focus on the true meaning behind each of the laws of motion. What do you understand from the first law of motion? Good job, Alex. The object's resistance to change is referred to as inertia. That's right, Alex. The more massive the object is, the more inertia it has, which means the more resistance it has to change, meaning it's more difficult to make it change its state of motion. So then, how do we overcome this stubbornness? Right again, Alex, an unbalanced force needs to be applied on the object in order to overcome its inertia. You got it, Alex. The more massive an object is, the more inertia it has, which means the greater the force that needs to be applied in order to overcome its force weight to change its state of motion.
Wait, what?
Glad you asked, Alex. Force weight is the force applied by an object based on its mass and acceleration due to gravity. Now, this can be expressed using the following equation. Fw, which is force weight, equals m times gravity. Now, m is mass. Good question, Alex. An object's force weight is applied perpendicular to the surface it makes contact with. So in this case, it would be straight down on the floor. Now, when we get into inclined planes, you're going to notice that this is very important information that you need to account for. Yes, that's right, Alex. Force weight is often used to determine how much inertia a particular object has since we're comparing it with other forces acting on it. Yes, Alex, the units for force are newtons, which is why 1 newton is equivalent to 1 kilogram times meters per second squared. That way, we can just abbreviate it using 1 newton instead of that long set of units. So on Earth, we calculate force weight by multiplying the object's mass times 9.8 meters per second squared. Good question, Alex. For the purposes of this class, it's going to be acceptable for you to round this value to 10 meters per second squared. Now, just keep in mind that the actual value is 9.8 meters per second squared. So to get a more accurate value of force weight on Earth, we would need to use 9.8 meters per second squared. So for instance, let's look at these two couches. Despite gravity being the same around them, their masses are different. Thus, their force weight will also be different. The bigger couch will have a force weight of 800 newtons, and the smaller couch will have a force weight of 250 newtons. Now, this means that a greater force is going to be required to overcome the more massive couch's inertia. Another good question, Alex. You need to keep in mind that each planet or moon is going to experience a different acceleration due to gravity, based on its size, which is a different formula and concept that we're going to discuss in later lectures. But for now, you just need to understand that acceleration due to gravity is different on other planets and moons. Thus, force weight would be different as well. Okay, now that you have a great grasp of Newton's first law of motion, also known as the law of inertia, let's discuss Newton's second law of motion, which states force equals mass times acceleration. Good observation, Alex. Since weight is a force, it does use the force equation in which acceleration is specified as acceleration due to gravity. So in other words, that g that we used in this equation is actually a. Okay, so based on the formula found in Newton's second law of motion, let's try to determine what acceleration would be obtained if both couches were moved using the same applied forces. Yes, that's right, Alex. The net force applied to these couches would be 15 newtons to the right. Okay, what else do we know? That's right, Alex. We know the mass of both of these objects, 80 kilograms and 25 kilograms, which means that we just need to solve for acceleration for both. Now, could we use gravity in this case? You got it, Alex. Acceleration due to gravity is only used when we look at vertical components of force, not horizontal, which is why we need to solve for acceleration using Newton's second law formula, in which we must move mass to the other side of the equation to leave acceleration by itself, resulting in that's right, Alex. This results in acceleration equals force divided by mass. So now all we need to do is plug in our known values and solve for A in both scenarios, which results in, right again, Alex. Now I want you to notice that the same net force was applied to these couches, but the couch with less inertia accelerated more than the couch with more inertia. So my question is, what net force would be needed to be applied to the couch with more inertia in order to accelerate the same amount as a smaller couch? That's right, Alex. We would need a greater force, and we can calculate it using the same equation from Newton's second law. But what variables would we use in this case? You got it, Alex. Based on our question, we would use the mass of the larger couch and the desired acceleration to solve for the required net force, which results in 48 newtons of force. In other words, you would need to apply 33 more newtons of force on the more massive couch to cause it to accelerate the same amount as the smaller couch did with only 15 newtons of force applied. I'm glad you asked, Alex, because we are including force weight into the net force. It's just that based on Newton's third law, the force weight of this object actually cancels out with its normal force.
Wait, what?
Normal force, which is basically the force the surface applies back on the object. Yes, Alex, based on the third law of motion, every action has an equal and opposite reaction. So in other words, when an object is pushing down on the surface based on its mass and acceleration due to gravity, which is what we call force weight, the surface pushes back on the object with equal force but in opposite direction. You got it, Alex. The downward force would be force weight, and the upward equal force would be normal force. Just think about it, Alex. If this wasn't the case, and the object's force weight was not balanced with a normal force, then in what direction would the object have to move? That's right, Alex. In order for the couch not to fall through the floor, it must be balanced in its vertical forces, which consist of force weight and normal force. Now, this is the reason that when we calculated the couch's net force, we didn't have to combine the vertical forces with the horizontal, because the vertical forces were actually balanced. Only the horizontal was unbalanced. Now notice that drawing so many forces on an object can get confusing, which is why in physics we draw free body diagrams instead. So instead of drawing the object in the center, we simplify it with a square to represent the object, and then draw all of the forces acting on that object. Great question, Alex. Let's say that we did want to consider friction in this free body diagram. How would we draw it? Good job. Friction would be drawn in the opposite direction of motion. In this case, the couch is moving to the right. Therefore, friction would be pointing to the left. Now, you need to remember, the size of the vector arrow corresponds to the magnitude, which is why normal force and force weight are equally sized arrows. But what about friction and applied force? How would you draw these? You got it, Alex. In order to overcome friction and get the object to move, the applied force needs to be greater than friction. Therefore, the arrow for friction would be smaller.
Oh, I get it now.
I'm glad you got it, Alex, because these three laws of motion will continue to be applied throughout the entire year. Well, this concludes our video lecture. Make sure you took good notes and
That's it. Have a great one.
Alex!